I just did today, which I also found very interesting. This one is a classification problem like the ones we've done before, but now in much more detail. So you download some data. This contains 70,000 images of handwritten digits from the census takers. They got a bunch of census forms and they digitized them and found out how people write letters. So you can print out some of them. The data is like this. It's a bunch of pixel values, just many rows of pixels, 70,000 rows with 784 pixel values in each row that go from 0 to 255 in grayscale, and then the right answer. The first one is a 5, the next one's a 0, the next one's a 4, and so on. You can view some of the images. So there they are. These are the images. So here's a 5, there's another 5, here's a 3, or is that a 5? There's a 7. So as you can see, some of them are clear, some of them are hard to read, and that's the point. This is what the images look like, and there are 70,000 of them. So break it up into training and testing sets, 60,000 to train, and the remaining 10,000 will be the test set. All right. Then you prepare binary data. What we're going to do, first we're going to make a binary classifier that just answers yes or no. So we're not going to sort it in all 10 categories. We're just, since the first one was a 5, we're going to just find the ones that are 5, and we're going to sort them into 5 and not 5 for the first binary category. So for that, this is binary data. So I just create a right answer matrix, which is whether it's 5. True for all 5s, false for everything else. Now I'm going to, here's the training set and the test set. I've got that parameter there. So if you print out some of the values, the training set has 5,400 trues and 54,000 falses. As you'd expect, it's mostly false, and the same thing for the test set. Only 1/10 of them are 5s and the rest are not 5s. So we're going to use a linear model. You have the input image. It has a bunch of pixels, and those are just combined into one neuron with linear weights, and you have this many parameters, and that's it. You then get a weight here, and if this score is above a certain threshold, that means it's a 5, and if it's below that threshold, that means it's not 5. That's how it works. So to train a binary classifier, it's incredibly simple. You just define an SGD, which is stochastic gradient descent, which is a way to improve the model with iterations where you just go down the direction and parameter space that's making it have a smaller error, and then you fit it on your training model. And so then you have some predictions on the first 3 here just to look at it. So it trains, it automatically trains until it feels like it's done training. I didn't specify the number of epochs. It figures out itself when it seems to have learned all it's going to. So it gets down here, the average loss gets down to 77. And then here's the answer. Prediction for image is 5, is true, false, and false. The first one was a 5, the next 2 were not 5, so it got the first 3 of them right. So it looks all right. So now we're going to talk about how you measure the accuracy of an AI. Now, one way to do it is with cross-validation. You split the training data into 3 folds, equal sections, then you train the model 3 times. You train it on 2/3 of the training data and set aside 1/3 to test it on, and you rotate them. So you do it 3 times and evaluate the accuracy 3 times using the excluded folds. This is called cross-validation. So here's how you do it. It's incredibly simple. You just use the cross-validation function, and you tell it 3 categories, score it by accuracy, and on you go. So the 3 accuracy measures are 95%, 96%, and 96%. That's how accurate these 3 cross-validation tests were. Now, that's possibly might sound good, but remember that 9 out of 10 of them are not 5. So if you just had a model that 100% of the time was false, it would be 90% correct. So being 96% correct is not that good. Anyway, so another way to determine how accurately your model is a confusion matrix. And here, what we do is we calculate the matrix, and this is how many were really not 5. Let me see, make sure I'm getting it right. Yeah, the first row is the non-5s. Okay, so the non-5s were correctly identified as not 5, 53,000 times, incorrectly identified as 5, 687 times. And the 5s were correctly recognized as 5s, 3,500 times, but incorrectly 1,800 times. So these are the errors, and here's the accurate ones. That's a much more accurate way to measure how this works, and you typically boil these down to a few numbers. Precision measures the accuracy of the positive prediction. It's how many true positives there were over all positives. So those are the ones that were found to be 5. So that's this. Here we had the ones that were identified as 5 incorrectly, and here's the ones that were identified as 5 correctly. So that's 83.7% of the 5s were correctly identified. Now recall, now there's a problem here. Suppose you raised the threshold to where it was very, very picky, and it would only call it a 5 if it was really, really sure it was a 5. Then this number would get really small. You would have very few non-5s detected as 5s. It would be a terrible model that wouldn't get very many of them right, but it would have a very high precision. It would very rarely have false positives. And as we've talked about elsewhere, false positives are not the only measure of failure. False negatives are also a problem, and that's what recalls are for. Recall measures the percentage of positive instances that were correctly predicted. So this is called true positive rate. So it's true positives over true positives plus false negatives, another mathematical equation. And so here, that was only 65%. So these two numbers together evaluate how good your model is. And you can combine them if the F1 score is a way to get one number that measures how good your model is, and that is a geometric mean. Precision times recall over precision plus recall multiplied by 2, because this will tend, if these were all 1s, it would be a half. And so if precision and recall are both near 1, this will be near 1. If you're good on both, you'll be near 1. If either one of them is small, it'll become small. So in this case, we had 83% and 65%, and the F is 73%. So that's one number to rate how good your model is. And you can calculate it directly with the model here and get it there. There's the 73%. So that sounds good, but you can adjust it. So by default, it will pick a central value to make the precision and the recall similar, because that's normally what you want in the general case. But suppose you don't want equal amounts of false positives and false negatives. Like suppose you're making a facial recognition scanner to detect thieves in a retail store. You want to detect the thieves, but you really do not want to accuse innocent customers of being thieves. So you really do not want false positives. You're probably willing to accept a higher rate of false negatives to make sure you don't get false positives. And this is true of a lot of cases, like, for example, detecting spam emails. You really don't want to throw away the good emails. And detecting viruses, you really don't want to flag innocent files as viruses. So you very often don't want equal false positives and false negatives. So the way you do that is you look at the neuron level. You have an output neuron that's got a level, and then by default, it will go in the middle where the precision equals the recall. But if you adjust the threshold to a higher level, then the precision will be better than the recall. If you make it a lower level, then you'll get more false positives and the precision will be less than the recall. So you can adjust the threshold and have different models that have whatever parameter, whatever properties you want. So here you can get the decision function from the model, and you can see here's the signals of the first 12 neurons, because I chose this because the first one is 5 and the 12th one is 5. So when it's 5, you get 2,000, and next time it's 5, you get 4,000, but when it's not 5, you get a number less than 0. So by default, it scaled it, so the default threshold is 0. So the default model will call all of these non-5 and those 5. But you could choose a higher threshold. If you chose a threshold of 3,000, then this one would not be detected as a 5. That would be a false negative, but this one would still be detected as a 5. So you would have more false negatives, but less false positives by having a higher threshold. All right, and so you can actually plot these parameters for all the threshold values, and here you are. If the threshold is near 0, you get these two approximately equal, precision and recall. If you move the threshold up, you get more precision and less recall. If you move it down, you get less recall, more recall, and less precision. By the way, if you get really high, then almost none of them are good enough. You're detecting almost none of them, and that's why you start getting noise here, because the actual number of detected values is very small. So anyway, and there's a flag defined, and I think then there's multi-class classification, the last thing, getting to the model we've done before, where I don't want just one yes, no for the 5s. I want to detect all 10 of them. And it turns out that all you have to do is use this SVC model, which is supposed to be a binary model, but if you tell it to train on non-binary data, it will automatically make multiple models. It can do it with 10 models to detect each of the 10, or it can do it with 45 models to compare each pair, and it will automatically choose which of those systems is more useful and perform it, and you get the predictions. So you get classifications in 10, and here's the classification. Here's the right number, and here's the number detected by the AI. And as you can see, I think it got all of the first 12 right. So, all right. And that's as far as I got on that one. But like I say, I'm going to have a lot more of these because this is the level of detail I'd really like to get to, where you really understand what's going into these models. So that's what I wanted to show you.